Today is going to be what I think is a really fun day. A lot of fun math today. The basics of sequences and series. We introduced the idea of finite geometric series on Monday. Now we're generalizing to more general series, which by default are typically thought of as what's called infinite series. But to understand series more fully, we have to talk about another topic first called sequences. At the most basic level, a sequence is just a list of numbers. However, what we're most interested in often is adding the numbers in that list of numbers, and that's called a series. To get things warmed up, we have a little story. Story of a very famous mathematician and scientist named Carl Friedrich Gauss. Carl Gauss, there he is, very famous mathematician and scientist who lived, you can see, late 1700s through the mid 1800s. One of the most famous mathematicians and scientists ever. You may have heard of Gauss before. The story goes, well, when Gauss was really young, like 2 or 3, that Gauss was correcting his father's books, his accounting stuff for his business. And then the story goes when he was 5 and he went off to kindergarten or whatever equivalent of kindergarten there was, that he was sitting in class one day, that you imagine it's like a one-room schoolhouse, and the class of kids, they're getting kind of wild, and the teacher was getting impatient and decided, okay, I'm going to discipline these kids. Get out your slates and your chalk and figure out the sum of the first 100 numbers, the teacher told them. And so they all got out their slates and their chalk and they started dutifully trying to figure out the sum of the first 100 numbers. Gauss was sitting there, heard the instructions, thought about it for a couple seconds, wrote down the answer, brought it up to the teacher. Gauss was right. Question is, how did Gauss do it? How did he figure out the sum of the first 100 numbers in his head in 2 seconds? Well, don't tell the punchline. I'm trying to get to the punchline. What did he do in his head? Okay, well, we're going to do it by hand, and it's going to take us longer than 2 seconds, but it's still kind of neat. Call the sum of the first 100 numbers S, say, and imagine writing the numbers out like this. So Gauss is imagining doing this in his head. And we'll put ... dots in there so we don't literally have to write out all 100 numbers. Perhaps this was the first time Gauss ever thought about it, perhaps not. Whatever the case, Gauss in his mind imagined writing the sum in a different way, using a trick. There are often tricks that people use in this context. The trick here is to rewrite the exact same sum in the opposite order. 100 plus 99 plus 98 plus 97, etc. The last 4 terms will be plus 4 plus 3 plus 2 plus 1. And then notice a pattern. If you add numbers vertically here, every time you do it, you get 101. Add these 2 equations. Of course, S plus S is 2S. So whatever we get on the right-hand side, it's 2 times the answer. It's 101 plus 101 plus 101 plus 101, etc. The last 4 terms are also all 101s. Every term is 101. And how many 101s do we have here? 100 of them. Because we were adding up 100 numbers on each row. And it's easy to do that because that's the same as 101 times 100, which is just 10,100. Now divide both sides by 2. S is 10,100 divided by 2 is 5,050. There is the answer. Go home and impress your parents. And it's easy enough that you could actually do it pretty easily. We're like adding up the first 1,000,000 numbers. or billion numbers if you want to challenge yourself a little bit, at least as far as mental math. You can do it. Isn't that amazing? There's some fun. There's our first bit of fun for the day. And the story is that's what Gauss did. Now, is it really true? Did Gauss really do this? Well, nobody knows for sure, but the point is it's believable since Gauss was such a child prodigy. Okay, probably other child prodigies today could think of this on their own as well without being told. So this is Gauss's story here. Gauss's story, or Gauss story here. Just a bit of a warm up, some fun with, well, this is a finite series, not an infinite series. We're going to work our way up toward infinite series. But remember, the basis of series is sequences. I said a sequence is just a list of numbers. Yeah, intuitively, though not really rigorously. Intuitively, a sequence is a list of numbers, and it's usually by default assumed to be an infinite list of numbers. An infinite list of numbers. Do finite lists count? Finite lists count? Yes. If we added the word finite instead of infinite in there, we could count it. Or we could say, hey, we have an infinite list, let's just stop somewhere. And that would be an example where we could consider a finite sequence. But mostly we're considering infinite lists, infinite sequences. Okay, let's take the simplest, or one of the simplest possible sequences imaginable. How about this infinite list of numbers? You've seen this before, I'm sure. Very famous sequence of numbers called the counting numbers, right? Because you use them to count 1, 2, 3, 4, 5, 6, 7, etc. I didn't miss any, right? Okay. Also called the whole numbers, also called the natural numbers. But I'm actually going to use a different phrase. I'm going to call these the positive integers. Positive integers. Yes, you could call them counting numbers. You could call them whole numbers. You could call them natural numbers. But I'm actually going to say positive integers. Say integers. I was at once at church and the pastor decided to bring some math into the sermon. And he decided to talk about numbers and he called them integers. And it just, I wanted to scream during the sermon, hurt my ears. No, not integer, integer. Okay. More, a little bit of fun. The integers have a special symbols. Just like the real numbers, you may have seen have this symbol, an R that's got an extra line in it. So the integers have a special symbol that have an extra line. It's Z actually with an extra line. Why Z? It's a German thing. The word Zahlen in German, which starts with a Z. Zahlen is, I don't think it's literally number, but it's related to numbers. I think it means integers. It's equivalent of integers. Numer is number. Zahlen is the word for integer. And that's why people use a Z. Anyway, so that's an infinite list of numbers, one you're very familiar with. How do you describe sequences? Well, you can list them out. If it's a pattern, you just say the pattern continues. Do they have to have a pattern? Not technically. They don't have to have a pattern, but usually the ones we're interested in do have a pattern. You can also define them by what are called direct formulas. And if I'm using the word direct as a direct formula, there must then be an indirect formula. And the answer is yes, there are indirect formulas as well, but we usually don't use that word. We usually call them recursive formulas, which I'll get to in a minute here. It's essentially pattern recognition when there's a pattern, at least with simple examples. S sub n represents, it's the symbol for the nth term of the sequence. The nth, and yeah, people do typically say that nth term of the sequence. When n is 1, it's the first term s sub 1. When n is 2, it's the second term s sub 2. The subscript is just keeping track of the term. When n is 3, it's the third term s sub 3. In this case, it's very simple. S sub n equals n. Right? The value of the sequence, the term itself, equals the position of the term, n, the subscript, first term, second term, third term, etc. And when you write it like that, it makes you realize that, technically speaking, sequences must be functions, because I could think of this formula as defining a function. And yeah, it does. This defines the sequence as a function. However, the domain of that function is not all real numbers when I'm saying it's a sequence. I mean, this formula could be thought of as being defined for all real numbers. I could imagine n to be any real number. But the point is, I'm purposely not doing that. I'm saying let n only equal 1, 2, 3, 4, 5, 6, etc. The domain is the positive integers. 1, 2, 3, 4, 5, 6, etc. And that's the typical domain that people use with sequences. Is it the only possible domain? No. Another typical domain is to include 0 and have a 0th term s sub 0. That's actually more typically what I do. But the book does it with starting with the first term. You even could do something weird and start with a -7th term. And the domain would start at -7 and then become -6 and -5 and -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, etc. You could do something weird like that if you wanted to. There's nothing stopping you. It's just not typical. If that's the domain and that's the formula, can we graph this function? Yeah. Graph it. Make this axis be n, this axis be, say, Sn. You are always, at least if the domain is all positive integers, plotting points above the integers 1, 2, 3, 4, etc. In this case, the outputs are also 1, 2, 3, 4, etc. So we plot these points along the line y equals x there, but we do not connect the dots. At least that's the convention. Now, some people connect the dots anyway, but if you do, it could cause confusion because it could make you think that this is defined for even fractional values of n. And that's not what we typically want to do. It's just how we're thinking about it. How about an indirect formula? Also called a recursive formula. Also known as, if you take differential equations in linear algebra with me next fall, as many of you will if you're engineering, for example, also called a difference equation, weirdly enough, not differential equation, but difference equation, in a way, for a reason I'll explain in a minute here. Not differential equation, but difference equations. But we will, in differential equations and linear algebra next fall, talk about difference equations as well. And I will typically call them difference equations in that class. Okay, just a word of warning there. Our book mostly calls it recursive formula. That's the one our book uses. A recursive formula says the nth term, or we might hope the nth term can be written in terms of the n minus first term. Any term except the first term can be written in terms of the previous term. Is that true here? Sure. To get from any one term to the next term, just add 1. So the arbitrary nth term, where n is bigger than 1, is the previous term plus 1. What's the previous term? Sn minus 1 plus 1. But only use this formula if n is bigger than 1, i.e., since n is a positive integer, n is greater than or equal to 2. But that doesn't completely define the sequence, because the first term doesn't have to be 1. I could start at 7 or something instead of 1. If S1 were 7 and this formula still applied, then S2 would be 8, and S3 would be 9, and S4 would be 10, and S5 would be 11. So I also need to specify the first term. It's not just the recursive formula, it's also the first term. S1 is 1. These two equations effectively are the recursive formula defining the sequence. Why is it sometimes called a difference equation? Well, at least one reason you could give is that this recursive equation could be written as a difference. Sn minus 1 equals 1. They're equivalent equations. You're saying the difference between any term and the previous term is 1. You got to keep adding 1 to get the next term. It's just another way of thinking about that. That's at least one reason why you could call it a difference equation. A little strange, but you could do that. All right, let's do a more interesting example. The sequence that has an infinite list starts out the same, 1, 2, but then the next one, the third term, is not 3, but 4 instead, then 8. See my pattern? Just keep doubling each time. And by saying keep doubling each time, I am implying what the recursive equation is. And in the end, we get pretty fast growth. You could even call it exponential growth. Yes, it is going to be related to an exponential function of n. So this is S1. This is S2. This is S3. This is S4, S5, etc. I put 1 comma, I better put the other commas. Direct formula. It's pattern recognition. Sn, right? These are all powers of 2. And take an arbitrary one like S5, 16 is 2 to the 4th. S6 is 32, that's 2 to the 5th. What should the power be here in this formula that I'm writing down? N minus 1. Again, look at the pattern. 1 is 2 to the 0, 2 is 2 to the 1st, 4 is 2 squared, second power, but the subscript is 3. S4 is 8, which is 2 to the 3rd. S5 is 16, which is 2 to the 4th. You got to make that subscript n minus 1 instead of n. And this formula applies for all positive integers n. An indirect or recursive formula is based on what I said a couple minutes ago. To get the next term, you're always multiplying by 2 or doubling every time. The nth term, if n is bigger than 1, is 2 times the preceding term. 2 times s sub n minus 1 when n is bigger than 1, i.e. n is greater than or equal to 2. Use that formula. And the first term, S1, is 1. I could have picked, again, I could have picked a different first term. I could have made S1 be, say, 3 and use the same recursive formula when n is greater than 1 to give me the sequence 3, 6, 12, 24, 48, 96, 192, etc. I'm still doubling every time, but it's a different sequence because I'm starting with a different first term. The recursive formula is the same, but the first terms are different. So it's technically a different sequence. You ever hear of the Fibonacci sequence? Fibonacci sequence. Does anybody know how it goes? Go ahead.
1, 2, 3, 5.
And the next one would be 21, 34, 55. The Fibonacci sequence starts with 2 1s. In other words, effectively 2 initial conditions. We say S1 is 1 and S2 is 1. Why? Just because we want to. And the pattern is, if you look at this carefully and try some things, you realize every term after the second one is the sum of the 2 previous terms. 2 is 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5. 13 is 5 plus 8. S3 is S1 plus S2. S4 is S2 plus S3. S5 is S3 plus S4, etc. So here the recursive formula involves the 2 preceding terms. Sn is Sn minus 1 plus Sn minus 2, although I guess I wrote that in the opposite order there. You'd only use this formula when n is bigger than 2, though, i.e. n is greater than or equal to 3. I'm assuming n is a positive integer. And you have to specify what the first 2 values are. This recursive formula and these 2 initial conditions completely define the sequence. And once again, I could get a different sequence if I picked 2 different initial conditions. Like maybe if I made, for example, if I made S1 be 5 and S2 be 6, and still use the same recursive formula, the sequence that's going to generate is 5, 6, 11, 17, 28, then 45, then 73, etc. The first 2 terms being specified, and then each of the other terms being the sum of the previous 2 terms. And you could call that not the Fibonacci sequence, but a Fibonacci sequence, I guess. Whereas Gauss lived a couple hundred years ago, Fibonacci lived in the ballpark of, I think, 700 years ago, perhaps. Fibonacci, let's look him up. So Fibonacci is a person. Yeah, lived actually even longer than that. Late 1100s and early through the mid 1200s. That's more like 800 years ago. And yeah, these are called the Fibonacci numbers, or Fibonacci sequence if you prefer. Amazingly, this has got applications. Fibonacci was thinking about rabbits reproducing when he was thinking about his sequence. That's what he was thinking about, is rabbits reproducing. I won't go into details. But it turns out the Fibonacci numbers come up in lots of fun situations, like in geometry, and also actually in nature. Like flower heads. You look at a flower head and you count the number of spirals, both the ones that go counterclockwise like this that are green, and the ones that go clockwise like this that are blue. It looks like there's more blue ones here. They're, I think, typically successive Fibonacci numbers. Question is why? Why are they successive Fibonacci numbers? And to tell you the truth, I don't know the reason. You'd have to get into the biology and physics of it, I guess. Why the genetics and the physics of growth forces that to happen. And it happens with all flowers, actually. It also even includes pine cones. If you look at a pine cone or a pineapple, even sort of head on, and you count spirals in different directions, they end up being Fibonacci numbers, the number of spirals. Let's get a little more practice with spreadsheets. Am I going to assign any problems with spreadsheets? Probably not for Friday, but maybe for next Monday, I might. So I'm going to put the Fibonacci numbers in a spreadsheet and show you something else kind of neat related to Fibonacci numbers. So I'm going to say S1 is 1 and S2 is 1. I'll put those in cells B1 and B2. Let's put the values of n in this column. So for example, remember, like I showed you on Monday, here in cell A6, I'm going to type equals A5 plus 1. Actually, I think you can just click and drag the actual original right corner down and it will automatically do that. But and let's click and drag this further down. And like I showed you on Monday, it keeps updating the formula every time. And so we keep adding 1. What is Sn? I don't need to use the dollar signs here for the absolute cell references because I'm not going to copy and paste these formulas downward. So I can just do equals B1 there and equals B2 here. And again, this gives me the flexibility of changing these numbers if I want. And then in cell B7 is where it gets interesting. I want to add the 2 preceding numbers. So type equals B5 plus B6. And notice I didn't literally type the B5 and the B6. I just clicked on the cells and it automatically came up. So this will do 1 plus 1 is 2. Click and drag it down. The next cell, it'll get updated to equals B6 plus B7, which is 1 plus 2 is 3. And it'll keep updating correctly. And you see the Fibonacci sequence. Fibonacci sequence does end up growing large pretty fast. For example, the 41st Fibonacci number is 165,580,141. Rabbits in the 41st generation, let's not go there. Okay. Here's the other interesting thing to show you. If you take ratios of successive Fibonacci numbers like this, creating yet another sequence, this sequence is also interesting. It's a sequence that has a limit. It doesn't grow forever and ever. It's got a limit that seems to be about 1.618033989. This is actually a special number in math. It even has a name. Does anybody know the name of this number? It's got a name. It's not pi. It's not E. It's not Feigenbaum's constant. That's another mathematical constant with a name. You know it?
Planck's constant.
It's not Planck's constant. That's a physical constant that in standard units is tiny. It's called the golden ratio. And what does it equal? It equals 1 plus the square root of 5 over 2. Why is that a special number? See it there? 1 plus the square root of 5 over 2. There, yeah, there's our 1.618033. It's a special number because it comes up in a lot of areas of math. You can see some basic things over here related to ratios of lengths of line segments in certain situations. Something called what's this? A continued fraction. It's a fraction that goes on forever and ever. Really? Yep, it is. Fractions that go on forever and ever. Yeah, they're called continued fractions. Oh boy, that sounds fun. Evidently, here's called the golden rectangle, where the ratio of this side to this side is the golden ratio. And I think there's some scholarly debate about this, conflicting experimental results, but some people claim that the golden rectangle, whose side lengths are the golden ratio, is the most aesthetically pleasing rectangle that there is. It captures the true essence of rectangleness, which means that when people are given options of like which rectangle they like best, they typically pick the golden rectangle. Is that really true? I'm not sure how true it is. And maybe experimental results conflict. But they actually do use it a lot in art and architecture, golden rectangles and golden ratios. And they show up in nature, like in flowers. Even the spirals themselves, I believe, are related to the golden ratio. Okay. It is a relationship to the Fibonacci sequence as well, like we just saw there. All right, fun, having fun today? I hope. Let's do another example. Oh, let's make this one an example with fractions. 1, 1/2, 1/4, 1/8, 1/16, 1/32. This is very similar to the previous example with powers of 2. Now I've got powers of 1/2, or if you prefer, negative powers of 2. Well, although the first one is 2 to the 0. You can see by the pattern here, these are negative powers of 2. Or again, if you prefer, positive powers of 1/2, like 2 to the negative 3 is also the same as 1/2 to the positive 3, which is the same as 1/2 cubed. So a direct formula, looking at the pattern. Sn would be 1/2 to the, this is the fourth term here. This is S4, right? There's the first term, there's the second term, there's the third term. 1/8 is the fourth term. The power of 1/2 is 1 smaller than the subscript, so this would be n minus first power. Which, once again, for emphasis, you could write as 1/2 to the n minus 1, which you could write as 2 to the 1 minus n, which you could write as 2 to the negative of n minus 1. Or if you prefer, you could also use properties of exponents to write this if you like. All these are equivalent formulas. They all work, okay? Any one of them is a correct answer. I'm just showing you there's lots of different ways you can write it. Recursive formula. To get the next term, we're always multiplying by a half. So Sn is going to be 1/2 times Sn minus 1. And the first term is 1. Those two things together are the recursive formula. Use this formula for n equals 2, 3, 4, etc. Here's a new question. Is it possible to use the recursive formula to find the direct formula if you didn't know it? Now, it's a simple enough situation here that you don't need to do that. But is it possible? And the answer is yes. And here's how. Use the recursive formula to find the direct formula. If we assume that n is bigger than 2, then n minus 1 will be bigger than 1, and I can use the recursive formula again. Replace the Sn minus 1 with 1/2 times the previous term, which will be Sn minus 2. Giving me 1/2 squared times Sn minus 2. Then if I assume n is bigger than 3, I could use the recursive formula again to replace the Sn minus 2 with 1/2 times Sn minus 3. If I assume n is bigger than, where am I? 4. So n minus 3 is bigger than 1. I could use the recursive formula yet again. Now imagine n is big enough that I can keep using this for a while. And eventually, by the pattern, I'm going to get to 1/2 to some power times S1. What is the power? Again, got to look at the pattern recognition. The power matches what I subtract from n. So I need to think of the S1 there, the subscript of 1 as n minus something. It's n minus 1. So the power has got to be n minus 1. But S1 itself is 1. The entire thing here is 1, right? That's what you see right there. So that simplifies to, well, we already knew 1/2 to the n minus 1. We found the same answer for the direct formula by doing this. Seems like overkill. Let's do an example where it's not overkill. So the example I'm about to do is harder. It doesn't look a ton harder when you first look at it, but it is harder. It is doable though. And once again, mentioning differential equations in linear algebra, where we consider difference equations. Next fall, you will be thinking about examples like this in that class, differential equations in linear algebra. Let's say Sn is, let's make it be 2 times Sn minus 1, but I'm not going to stop there. I'm also going to add 1 to it. And let's say the first term is something a little different, maybe 5. The question is, can I find a direct formula? Let's do the exact same thing we just did. This kind of process in this new situation. It's going to be harder, but it is doable. We will be able to get the answer. So this formula applies when n is bigger than 1. So start by assuming n is bigger than 1, so I can use this. Then use it again. So in effect, assume n is bigger than 2. So that I can use it on this thing. Replace Sn minus 1 with 2 times Sn minus 2 plus 1. Simplify, but don't simplify too far. I mean, yes, 2 times 2 is 4, but it's also 2 squared. Let's leave it as 2 squared. The reason is because there's going to be a pattern. 2 times 1 is 2, and then we have the plus 1 there. Now use it again. Pretend n is bigger than 3, so that n minus 2 is bigger than 1, and I can use this formula again. Replace Sn minus 2 with 2 times Sn minus 3 plus 1. This entire thing gets replaced by this entire thing. Don't forget your plus 2 over here and your plus 1. And of course, yes, 2 plus 1 is 3, but I'm going to leave it as 2 plus 1. Distribute the 2 squared through. 2 squared times 2 is 2 cubed. Two squared times 1 is 2 squared. Starting to see a pattern here. Let's try it once more. Assume n is bigger than 4, so that n minus 3 is bigger than 1. Use the recursive formula again. This thing is the same as 2 times Sn minus 4 plus 1. It equals that. Distribute the 2 cubed through the parentheses to get 2 to the 4th Sn minus 4 plus 2 cubed times 1. Don't forget the other terms. All right, pattern recognition. By this pattern, it seems like we could write Sn as ultimately 2 to some power times S1, where once again, the power here has to match what we subtract from n. 1, once again, is n minus 1. Therefore, this power of 2 must be n minus 1. By the pattern. And then the other terms are powers of 2 as well. Lower powers of 2, we'd have 2 to the n minus 2, 2 to the n minus 3. We keep lowering the power of 2 by 1. And this is you could call this a direct formula for Sn, but it's not super simple. However, it can be simplified, because this is a finite geometric series. So if we use the formula for the sum of a finite geometric series from Monday's class, we can simplify this. What was that formula? That formula was a plus a times x plus a times x squared, etc., through a times x to the n minus 1 power was equal to a times, in parentheses, 1 minus x to the n over 1 minus x, if x is not equal to 1. It's probably simplest to think about this geometric series from right to left. You could do it from left to right, but it's probably simpler to think of it from right to left. Think of the 1 as the a, and what is x going to be? Compare these. Here I'm going from right to left. Yeah, x is 2. 2 is a times x, 1 times x. X has to be 2. 2 squared is 1 times x squared. 1 times 2 squared is 2. 2 squared, excuse me. 2 cubed is 1 times 2 cubed. So a is 1, x equals 2, and remember back here we had n terms that were being added. Here actually we got n minus 1 terms. right? Because that power is n minus 2. I'm not including this part here as part of it because the S1 equals 5. If the S1 were a power of 2, perhaps we could, or if it were 1, then we could definitely think of the whole thing as being a geometric series. But I'm not including that. N minus 1 is the number of terms. So that's the meaning of the n here, is it's the number of terms. So these things imply that Sn is, okay, I'll put the 5 there, 5 times 2 to the n minus 1 plus all this becomes that. A is 1, X is 2, n minus 1 is the number of terms. Can this be simplified? Yes. That's a negative 1. 1 divided by negative 1 is also negative 1. Multiply this thing in parentheses by negative 1, you can switch the order. You get 2 to the n minus 1 minus 1. And then these two terms can be combined to give 6 times 2 to the n minus 1 minus 1. There is the simplest direct formula for Sn. You use this for n equals 1, 2, 3, etc. We should test it. How? This is good to do on your homework. Test it. Is it really working? Let's go back up to the recursive formula. I will show you the direct formula again if you didn't quite get it copied down. This the recursive formula implies that the sequence is first starting with 5, then 2 times 5 plus 1 is 11. Then 2 times 11 plus 1 is 23. 2 times 23 plus 1 is 47. 2 times 47 plus 1 is 95, etc. Notice that these numbers are all 1 smaller than a multiple of 6, right? 5 is 6 minus 1, 11 is 12 minus 1, 23 is 24 minus 1. Oh, this is looking good. Do we have a match? For example, when n is 5, that's the 95 there, that's the S5. Plug in n equals 5, you'll get 6 times 2 to the 4th minus 1 is 6 times 16 minus 1. 6 times 16 is 96. Minus 1 is 95. We got a match. And you could test other numbers as well. This does work. Remember that differential equations had solutions? We talked about that a tiny bit earlier in the semester. Difference equations, recursive formulas with initial conditions also have unique solutions. There it is. This is the unique solution of this recursive formula, this difference equation. And again, I could write it as a difference. I could subtract 2Sn minus 1 from both sides to write the left side as a difference if I wanted to. You solve differential equations by integration. You solve difference equations by recursion. This is not always possible to do, by the way. It worked here, but there's plenty of even fairly simple examples where it just doesn't work. There's no way to figure out a pattern for it. Just like when you integrate, it's not always possible to do by hand with a symbolic closed form expression involving elementary functions like trig functions and exponentials, etc. Sometimes with integrals, we got non-elementary functions like ERF or Fresnel, things like that. Still fun? I hope so. I think it's kind of fun. Let's keep going. I should mention though I forgot to mention in the first class, something that comes up in section 9.2 that's important here is this expression, which equals a over 1 minus x times 1 minus x to the n, goes to a particular number as n goes to infinity if x is between -1 and +1. Because this expression, x to the n, this goes to 0 as n goes to infinity if x is between -1 and 1. Right? You take a number close to 0, more precisely between -1 and 1, higher and higher powers are going to get closer to 0. Right? 0.9 to higher and higher powers gets closer and closer to 0. And therefore, the entire expression approaches a over 1 minus x times 1 minus 0, or just a over 1 minus x if x is between -1 and 1. Another way to write the condition that x is between -1 and 1 is to say the absolute value of x is less than 1. That's really important for infinite geometric series and comes up in section 9.2. But what I want to talk about mostly for the rest of class today is more general kinds of series, not just geometric. I will come back to a geometric example, but in our last 17 minutes here, let's talk about general series. General, I'm going to put the word infinite in there again, but this time I'm going to put it in parentheses. If you just use the word series in math or general series, it's typically assumed it's infinite. That's why I put infinite in parentheses. And the word series in this context is synonymous with sum. But these are infinite sums, typically. These are effectively synonyms in this situation. However, there's a dirty little secret that I'm going to share with you when we talk about series, infinite sums. Here's the dirty little secret. We're not literally adding up infinitely many numbers. Not literally. Why not? Because nobody can add up infinitely many numbers. It's impossible. You can't keep adding forever and stop, because by definition, you're going forever. So what's this about? It's about, and I'm serious here, it's about pretending to add up infinitely many numbers. And I'm dead serious. This is part of what makes calculus confusing. All this pretending, all this hand-wavy stuff. More caveats. This pretending can be made rigorous. We can make rigorous what we mean when we say we are pretending to add up infinitely many numbers. We can make it completely rigorous, what it means. That's one issue to clarify. A second issue to clarify is, even though we're only pretending to add up infinitely many numbers, it still ends up being useful for real life, even though in real life you can't literally add up infinitely many numbers. Wow. Isn't that wild? I will say those kinds of things again. So if you didn't write it down, well, you can watch the video, but I will say those kinds of things again, so you don't have to just remember it right now. First of all, the symbol for the infinite series involves our old friend, the summation sign, capital sigma. The index of summation is called lots of different letters, sometimes I, sometimes J, sometimes K, sometimes M, sometimes N. The book uses I. It's a summation. I goes from 1 to what? Infinity of A sub I. And A sub I is called the ith term of the series, or the general term. I used nth before. This is ith, right? What is I? Well, it's a variable effectively. It could be 1, it could be 2, it could be 3, it could be 4, it could be 5. If I were 10, then the ith term is the 10th term. So we can write it with the summation sign. It's typically more comfortable for people if they write it out without a summation sign. A1 plus A2 plus A3 plus A4 plus A5, etc. Now these A's, if I put commas between them instead of plus signs, would form a sequence. That would be an infinite list of numbers. But I'm not putting commas between them, I'm putting plus signs. I am imagining, I am pretending to add up infinitely many numbers. But wait a minute, can you really do this? I mean, what if all those A's were 1? Then I'd be doing 1 plus 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 dot, dot, dot. Adding up a bunch of ones forever. And what do I say the answer is? Infinity? Wouldn't that make the most sense? Yes and no. Okay, what we mostly want to think about here are situations where we actually get a finite answer. Such series are called convergent series, analogous to convergent improper integrals. If we do have a series such as 1 plus 1 plus 1 plus 1 forever, yeah, some people might say, okay, it equals infinity. But remember, for us, infinity is not a number. In some other math classes, infinity can be considered a number, but not in our class. It all depends on your perspective. For us, infinity is not a number. We don't say 1 plus 1 plus 1 plus 1 plus 1 dot, dot, dot equals infinity. We just call it a divergent series, analogous to divergent improper integrals. And just as we had comparison tests with improper integrals, so there's comparison tests with infinite series. But before we get there, we need to say, what does it mean for the series to converge? We have to consider the corresponding sequence, not series, but sequence of partial sums. Partial sums. Corresponding sequence of partial sums. What are those? So it's a sequence, not a series, just a list of numbers. I'm going to call them S1, S2, S3, etc., where S1 is the first term, A1. S2 is not the second term, A2. Instead, it's the sum of the first 2 terms. Partial sum. S3 is the sum of the first 3 terms. S4 is the sum of the first 4 terms, etc. SA sub n is the sum of the first n terms, which I could write with dot, dot, dots. Or I could write, if I want, with a summation symbol, a finite summation. I goes from 1 to n instead of 1 to infinity. A sub I. This is called the first partial sum, even though it's not really a sum. This is called the second partial sum. This is called the third partial sum. The fourth partial sum. In general, this is the nth partial. This was the ith term of the series. This is the nth partial sum. This entire thing. These entire things. And these are all finite sums, so they make perfect sense. Okay. And here's the punchline. If in general S sub n converges as a sequence, the numbers get closer and closer to some limit. You can't get away from limits in calculus. It's what calculus is all about. Derivatives are based on limits. Integrals are based on limits. Improper integrals are based on limits. Series are based on limits. And that's what makes it rigorous. You got to precisely define what a limit means. If Sn converges to some limit, call it, say, S, as n goes to infinity. And when I write as n goes to infinity, I'm not saying infinity is a number. I'm just saying n gets larger and larger without bound. Then we say the series also converges to S. And we write the infinite sum to actually equal S, as if we have added infinitely many things. As if, even though we actually haven't. Right? I didn't add up infinitely many things there. I just defined what it means to pretend to add up infinitely many things. The bigger question is this useful? The answer is, as always, yes, it is. You could say S is the limit as n goes to infinity of Sn. You could write that as well. Of Sn, not A, not An or Ai for that matter. It's the limit of the S's, the partial sums. It's related to the A's. The S's are related to the A's, but they don't equal them except for the first one. Super important to understand both the relationship between the A's and the S's and also the distinctions between them. This is a key place where people get confused. You've actually dealt with infinite series since 5th or 6th or 7th grade without knowing about it. For example, when you consider the number 0.1 repeating, oops, 0.1111111 dot 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 forever and ever, you're really thinking about an infinite series without knowing it. Because by definition, what this infinite repeating pattern means is 0.1 plus 0.01 plus 0.001 plus 0.0001 plus 0.00001, etc. Or if you prefer, 10 to the negative 1 plus 10 to the negative 2 plus 10 to the negative 3 plus 10 to the negative 4, etc. The question is this a convergent series? And what does it converge to? I hope you remember 0.1 repeating equals 1/9. This better converge to 1/9, does it? Yes, it does. Why? It's actually a geometric series. And notice I did not put the word finite in there. It's an infinite geometric series, which is assumed if I don't put the word finite in there. With first term A equal to 0.1, common ratio X also equal to 0.1. And what's N? Well, N is infinity, and infinitely many terms, I'll just say. Therefore, since the absolute value of x is less than 1, it converges to this by this argument here. A over 1 minus x. A simpler formula than that. Things get simpler at infinity. That's one reason why it's useful to pretend to add up infinitely many things, because things actually sometimes get simpler at infinity. This equals a over 1 minus x, 0.1 over 1 minus 0.1, 0.1 over 0.9, which, yes, is 1/9. Of course, in 5th, 6th, or 7th grade, your teacher might have shown you another way to figure this out. That's also kind of fun. A trick. If you say s is 0.1 repeating, and you multiply s by 10 to say 10s is 1.1 repeating, and then subtract one equation from the other, 9s equals 1.0 repeating, because all the ones after the decimal canceled, which is 1, so s is 1/9. That's a little quicker way to confirm the answer, though maybe a little bit more hand wavy. Because can you really cancel all those ones after the decimal? Well, yes, but it might seem a little fishy. Same answer. Probably did it in that way, 5th, 6th, or 7th grade. But now we're doing it this way, and you should be able to do it this way. Final topic for the day, 2 minutes, is that there are some infinite series where the partial sums are very difficult to simplify, but it turns out you can sum the series anyway using various tricks. The most famous of these is called the Basel problem. Don't say Basel, say, or Basel, I think it is. Basel problem. Basel, after Basel, Switzerland. Solved by Euler. Don't say Euler, that hurts my ears. Even though I just said it. Say Euler. Another very famous mathematician. Actually, Gauss was both a mathematician and a scientist. Euler, you could call him a mathematician and a scientist, but he was more of a mathematician. Add up the reciprocals of perfect squares. So what would this be? It would be, hang on here just a second here. 1 plus a 4th plus a 9th plus a 16th plus a 25th plus a 36th, etc. Turns out very difficult to find any simple formula for the partial sums, even though the series itself looks nice and simple. However, it does have an answer, and Euler figured it out using a lot of tricky math. And here it is, drum roll. Boom, pi squared over 6. What? Pi? Pi? Yes, pi. Pi squared, in fact, over 6, in fact. Euler, this is one of Euler's most famous results, and it spurred mathematicians to want to study infinite series, because they looked at that and they're like, why did that happen? It's amazing. I'll share a 3 blue 1 brown video with you where he explains this in some creative ways. Have a good day.